You know, what I tell my students at Columbia, that I'm not a good teacher, but I'm sure you're very good students. So one of the skills you learn as a student is how to extract more from a bad teacher, right? So you have to use those skills. So I think that every question you ask will make things better. At some point there could be too many questions, but I don't think we'll reach that point. So you should interrupt. So I will talk a little about regression, which is sort of our basic tool for understanding the world. Are they returning, or did they just decide that these are the first hour was, they got so much out of that first hour that they wouldn't want to, it would be too much after that to have anything more, learning more than that would be overwhelming. Okay. So, you know, linear regression, I'm not going to talk about how the formula for computing linear regression, but how do we, first, how do we interpret the models, and then how do we build them, and how does statistical significance fit into all of this? I start with a simple example, which I regret, well, okay, so I apologize here because I didn't convert this into centimeters. So this is height in inches. So an inch is 2.5 centimeters. For every inch of height, people earn 6% more money. And you know, when I teach this, when I do this for my classes, I actually ask the students to work in pairs and to draw this regression line. And do we have chalk? Yeah, we do. So this is like, it's interesting to see people do this. I won't make you do this, but I show people this output and I say you have to draw the regression line, and then I walk around the room and I see what people do. And so they sort of start with this. They have they go like, well, here is 5 point. Well, I should write bigger. Sorry. This is excellent chalk. It's very soft. You have the finest chalk. Don't use more than one. Okay. I'll use a little chalk because I'm afraid of if I did anything to the chalk. Okay. And then they'll do this and they'll say 5.74, and then they'll draw this line and they'll say the slope has to be 0.06, and then they'll look here. And it's like, it's not going to happen that way because, you see, like, height, most people are between 60 and 80 inches tall. If you start like saying here people are between 60 and 80, and you don't really want to do that. Like you sort of want to you sort of want to start by going from 60 to 80. Which means you sort of have to figure out, so you actually have to do 5.74 plus 60 times 0.06, and well, 6 times 6 is 36, and that's 6 times point, like, so you sort of have to figure out where it goes here, and then you compute 5.74 plus 80 times 0.06, and that's up here, and you figure out what these are, and you can draw this line. Like, now this is silly, right? I mean, you're above all this, but you're not, okay? Because you'll read reports, and people are going to have much more complicated things than this. You have to sort of know how to interpret this, and I think that I think that the deterministic part of the model is very important, and people forget that. Like, you look at this, and I think all you noticed was that, well, this is 6 of these, so therefore it's statistically significant, and which is fine. It's fine to know that. There's not much uncertainty about that coefficient, but the magnitude is going to be important also. So you really have to be able to visualize these things. And this is the simplest model there is. Well, okay, so I threw sex in here because, of course, taller people make more money, but men make more money than women. So now here's the regression. So here we can look at this and say, well, just looking at that men have, so this is on the log scale. So men's income, or like women's income multiplied by e to the 0.42, which is sort of like 1.42. It's a little more than that. So men make something more than 40% more than women if you're comparing two people of the same height. And then for every inch now, it only corresponds to a 2% increase among men or among women. I actually find this coefficient for male sort of hard to interpret. Because it's not clear that I want to be, if I'm comparing a man to a woman, it's not clear that I want to compare a man and a woman who are the same height somehow, because then I'm comparing a short man to a tall woman, which doesn't seem quite right. So the interpretation of these coefficients can be difficult. Of course, the R squared is only 0.09, which is good, right? Because if the R squared was a big number, then that would mean most of your earnings could be explained by your sex and your height, and that's not really appropriate unless you're a basketball player. So it's a good news there, the low R squared. Now I have another example. This was one of my favorite examples because I don't know anything about it, so I feel like I could really sort of approach it in a generic way. It was a data set of the yields of the weight of the leaves of a bunch of mesquite bushes. They use the leaves for something, and they have these each bush looks like, oh, it's so smooth, the erasing too. This is just the greatest blackboard. So you have this bush which sort of looks like this, and they have the diameter, how far the bush is along the long axis and the short axis, and then how high the canopy of leaves is, and then the total height of the bush, and then the number of stems here, which is typically 1, but sometimes it's more, and then there were 2 different groups of bushes that were being measured, and it was the goal was to predict the weight of the leaves from all these things. So the first thing you sort of know is you should take the log of everything. Well, because they're all positive numbers. Well, you don't take the log of the group indicator, but you take the log of everything else. That means that it's a multiplicative model. So somehow the weight of the leaves, the total weight, having the bush be a little higher, say, could multiply the leaf, would be expected to multiply the total amount by a certain amount, not to add a certain amount. So it should all be in the log scale. I'm sort of jumping ahead though, so I should say here's the linear model first. So the linear model said that for every meter that diameter 1 was bigger, you got 190 grams more leaves. For every meter diameter 2 was longer, you got 371 grams. Some of these things are significant and some aren't. It predicts pretty well. The R squared is 85%. Now, as I noted, as I just said, actually, this is not a good model with these funny negative numbers. And if you're not careful, you could predict a plant has a negative weight of the leaves, which isn't going to be the case. We switch on the log scale. Now, interestingly enough, like the signs change. So if you look at this on the log scale, do you notice everything has a positive coefficient? Now, I'll get to the other columns in a minute. The only thing that's a negative coefficient is the group indicator, because group 2 has less leaves than group 1. But you notice on the original scale, we actually had a negative coefficient. So in the original scale, a taller bush had less leaves, but on the log scale, that's no longer the case. I'm just pointing this out because I think often that happens to you. Have you ever raised your hand if you've ever done a regression and you then like do a transformation and the sign changes and you don't know what to make of it? Has it ever happened to you? Nobody? Okay, the two of us in the room have had this experience. Three, maybe. So it happens. Well, you know, sure. Yeah, you have to look at the confidence level. It's not statistically significant. No, but the point is, that's, sure, we should look at there's a lot of uncertainty. So this has a standard error of 0.12. But you could have a sample of size 100 million and everything would be statistically significant. The signs could still change. The point is that the interpretation, the linear model and the log model are just different. In this case, the linear model just doesn't make a lot of sense. It doesn't really make sense to say that having a little more increases the leaves by a certain number. Everything is going to be proportional to everything else. So yeah, the R squared is the same, but the model just makes more sense. So you want a model that makes sense, if possible. So I didn't really, sorry, let me go back. This model sort of has too much in it in the sense that, like, a lot of these things aren't statistically significant. It's not clear what to make of this. For example, look at canopy height and total height. So this is saying if you increase the canopy height but keeping the total height the same, like sometimes it's hard to interpret some of these things. So I decided to rebuild the model from scratch. So I created this thing called canopy volume, which was the long diameter of the canopy times the short diameter of the canopy times the height of the canopy. The canopy is where the leaves are. So it's a total volume of the leafy part of the tree. So to my mind, this was the simplest model that could make sense. You just compute the volume, you treat the tree as a cube, you know, and you compute how much volume is there. That's sort of how much leaves you should have. And so then you get this coefficient. The volume of the canopy, how much leaves you get is like, sorry, the weight of leaves you get is like the volume to the 0.72 power, right? In economics terms, the elasticity of canopy volume is, when you're predicting the weight of the leaves, is 0.72. So, I mean, this seems sort of funny. Like, I was sort of expecting to see a coefficient of 1, because a coefficient of 1 would say, on the log scale, would say that the leaf weight is proportional to canopy volume, but it actually goes like volume to the 2/3 power. Then I thought about that, and I thought maybe that actually makes sense. Do you know why I think a 2/3 power sort of makes sense here? Do you know, like, where are the leaves on a tree? The leaves are on the surface, right? Like, there aren't any leaves on the inside because they don't get any light. So if you sort of think about it, the tree volume is this sort of spherical thing. The surface area is roughly the 2/3 power of the volume. So there you go. I mean, it's like 0.67. So it didn't have to be that way, but that was sort of gave me a warm feeling that I was sort of on the right track, that I understood it. In a way that I just wasn't getting a warm feeling from these numbers. Now, this has an R squared of 0.89 and this is 0.8, and that's a big difference. So I'm certainly throwing away a lot of information by only using this, but I feel like I'm getting a little closer to understanding things, which is pretty good because it's something I don't understand at all. Right? Now, in your training, you know, the funny thing is, okay, canopy volume is a linear, on the log scale, the log canopy volume is a linear combination of log diameter 1, log diameter 2, and log canopy height. Right? Because it's the product of these things. So on the log scale, it's the sum. So what I've done is simply take a linear combination of my predictors. Now, as you've learned when you took linear regression, doing a linear combination of a predictors really has no effect in doing a linear regression. A linear transformation of predictors doesn't do anything. But it actually does do something here because it gives me new ways of understanding things. And so I'm trying to emphasize that a model, you have to sort of ignore the tough guy talk you heard. Like when you took statistics, you hear lots of tough guys. Everyone, like people, economists and statisticians always trying to act how tough they are. So they'll say things like, all I care about is prediction. Like, I'm not a philosopher. All I care about is prediction. Prediction's the only thing that matters. Like, this is BS. Okay, that's not true. Prediction's not the only thing that matters. That's not why we're running regressions all the time. We're trying to understand things. You have a lot of, and then people say, well, the transformation doesn't make any difference because it's blah, 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 mathematical, blah, 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 matrix, blah, blah. But that's not true either, because you have a lot of choices in setting up your model, what variables to include and what variables not to include. So I'm going to start with this variable, but now I'm going to add more. Okay, so I created another variable called canopy area, and the canopy area is the product of the two linear dimensions here. And look at this sort of actually makes sense. So the canopy volume is a positive coefficient, but so does canopy area. Because if conditional on volume, area is sort of good, like because it's more spread out, so it should have more leaves. Then I have a variable called the canopy shape, and the canopy shape was the ratio of the two dimensions, the long dimension, the short dimension. So the idea is that the less spherical it is, the less leaves you have, which sort of makes sense too. Then I put total height back in the model, and the idea is that a taller tree maybe should get more light than a shorter tree. And then these other variables, which I don't fully understand, but were in there from before. So again, now this actually is the same as our model from before. It's just with linear transformations, but I just understand it better. This sort of all makes sense to me. I can interpret each coefficient. Now, there's a lot of noise here. I don't really believe this is exactly 0.39. I don't even know that it's positive, but it sort of makes sense to me, so I can go with it. And then you can play around. I took this model and then I got rid of this density variable because I don't really know why the number of stalks would predict the leaves, and it's not anything like statistically significant. It seems reasonable to take it out. So I got rid of this one, and now here's a model which I sort of like. It's my final model. Is this correct? It's not correct, right? It's just, but it's a reasonable summary that I understand. I think we need to do a lot of this is sort of common that we need to understand our model doing a lot of transformations. So that's the point of this particular example. There's no magic answer. I don't have a twist at the end. So in summary, even the simplest models like regression of earnings on sex and height, even there, the interpretation of the coefficient is not obvious. Transformations, doing a log transformation can be very important, and even a linear transformation can help. Theory would suggest otherwise, but doing linear transformations can give us a better handle on what our model is. Another example, this comes up a lot, is you're predicting something, and in my world, let's say I'm predicting elections given economic indicators, and I have 5 different economic indicators. Or I'm predicting students' performance given 5 different test scores. Or you can think of your own example. If you throw all of them in, then nothing is statistically significant. You could do some sort of factor analysis, but that's sort of one more thing to explain in life. People will say, well, if I have 5 predictors, which one should I use? I might use the average of all 5. So I might rescale them to make sure they're all in a 0 to 100 scale, and then take the average and say, this is my average economic indicator, and use that. Now, is that correct? I don't know that it's correct, but it makes more sense than using any single one. But the point is, I would never get there by just playing around with stepwise regression and statistical significance. The only way I get there is I have to sort of step out from behind the statistics and try to study what I'm doing. Use subject matter information. The same way here, we actually looked at the tree to understand what was going on. It couldn't have been done automatically. Now I have a story about logistic regression. And I have an example from our research from several years ago. I guess it was like 10 years ago now, on the drinking water in Bangladesh. We're going to talk about how we built a model and added interactions and compared models. So here's the background. Bangladesh, as you might know, gets flooded a lot. In fact, if you ever want water in Bangladesh, all you have to do is dig a hole, and after about 2 feet, you'll get water. So it's not really a problem. You'll get fresh water, but in the last few decades, there's been problems because they have a lot of animals that poop in the water, so then you drink the water and you get sick. And so a couple decades ago, some international do-gooder type organizations came in and had this idea that if the people in Bangladesh could just dig deep wells, so what they do is they pound plastic pipes into the ground and then use a pump to suck the dirt out of the pipe. And then when you do that, you get water coming in from 50 feet underground, coming straight through the pipe and gushing out. And you get a well, and you get no poop in your water because there's no poop 50 feet deep, and the dirt serves as a natural filter for the microbes. So you get fresh water. And over the next few years, this is actually the number of wells in a small province of Bangladesh, not a province, a small, tiny little area of, in the country as a whole, I think they dug 10 million wells or 20 million, some huge number of wells. And here they are pumping the water. It doesn't gush out, you have to pump it out. But like it's coming out from 2 feet deep, so it's easy to pump. Here's someone pumping the water, and they also use it for agriculture, for irrigation. Now, the bad news is, as you see in this picture, a lot of the wells are unsafe. They don't have poop in them, but they have arsenic, which is bad for you. It causes cancer. Here's a map of the country. The red areas show the places in the country where there's high arsenic in the drinking water. The arsenic in the drinking water in Bangladesh, it's just one of these unlucky things. It's not like some company spilled arsenic into the ground and it's pollution. It's just natural. It's a natural element in the earth. And in only a few places around the world, the arsenic is loose in the water and you can drink it and it can give you cancer. And like, if you dug a well here, I'm pretty sure that if you dug a well here in Rome, you would not have arsenic in your water. The arsenic binds with other things and it's completely safe. Bangladesh happens to be one of the few places in the world where there's an arsenic problem. And also it's one of the few places in the world where the international organizations told them to dig 10 million wells. So people are getting cancer, and like people feel bad about it. Like they told people to dig wells and now they're getting cancer. It's like a bummer, So we study this in various ways, but what I'm going to tell you here has to do with this little area, which you see, look, this says 3 kilometers. So it's a small area, and it's a small area here. They went and measured all the wells. They did this in other places, but I'm just demonstrating here. They did a survey. The red were the wells with really high arsenic levels. Green were low, and yellow were in between. They did this. They purposely picked an area on the frontier here. Do you see? If you picked an area here, everything would be green, and there'd be nothing to say. And if they picked an area here, everything would be red, and the only message would be, don't dig a well, right? But as you can see from this map, there's a lot of parts of the country where there's a very obvious short-term solution, which is just if you have a bad well, drink from a nearby well. And maybe you should dig nearby and you might find a safe well. So our project had to do with recommendations to people about where they should dig. We created some sort of cell phone app like not a smartphone. This is like, pre-smartphone. But we created one of these things where it used your GPS and you say, I want to dig a well, and it would say how deep you should dig the well, so it's likely it would be safe. So there's lots of statistical analysis. Grazia's twin sister worked on this project, our other Italian postdoc, and who you never met, right? You never, no. Yeah, no, but you never met her. She's Italian. She's the other Italian, yeah. Okay. And she looks like you, though. It's another black-haired, yeah. And so, anyway, what I'm going to tell you about here is a survey that we did where we asked people, would you switch if they actually surveyed people who had red wells, and they said, would you consider switching to a neighbor's well if it was safer? And I'll tell you what we found. So here's another. They're digging wells. I think enough. Okay. So we're going to predict whether people said they would switch wells based on how far they would have to travel to get to the nearest safe well, the arsenic level of their current well, their level of education, and their membership in community organizations. And so just to make it clear, the longer you have, the larger your distance to the nearest safe well, the less likely you'd switch, because it's more effort to switch. The higher your arsenic level is, the more likely you should switch. Presumably, having more education should make you more likely to switch, because you'd just be more accepting of the idea that even though the stuff doesn't taste bad, it could kill you, or just having more education is perhaps predictive of having a longer time horizon for various reasons, maybe more wealthy also. None of these people are rich, though. These are people in a set of villages. And finally, membership in community organizations, that we thought that if you're a member of a community organization, you might be more likely to switch just because you'd be a more social person and be willing to ask somebody to use their well. It turned out that was not predictive of switching in the data. Here's our regression. This is logistic regression, the probability of switching just as a function of distance. Now in this case, it was distance in meters to the nearest safe well. So in our data set, this is not the best graph. Each dot here represents a person or a household. So there's a lot of dots here, they overlap, and then out here there are very few dots. Almost everyone is within 50 meters, or most households are within 50 meters of a safe well, and almost all of them are with 100. A few of them are as much as 300 meters away from the nearest safe well, just because they happen to be surrounded by a bunch of dangerous wells. We gave people this information. We actually told them how far the nearest safe wells were, so they didn't have to guess this. This is the result of the logistic regression. Further away you are, the less likely you are to switch. Perhaps surprisingly, even people who are next door to a safe well often don't switch. I don't know what to say, except it seemed funny to me, but then I thought, well, I mean, in the United States, it's not like I share anything with my neighbor, right? So it's not clear that Bangladeshis should be so much different. I guess it's a big social cost to ask somebody. Statistical messages here. I coded distance as distance. I created a variable called dist100, which is the distance in 100-meter units, because I like to have a natural measurement. So if I had said distance in meters, then it would have been 0.0062. So for every meter away, it changes the logit by 0.006. How do you interpret 0.0062? It's impossible. Or I could have done kilometers, but kilometer is too big because nobody's a kilometer away. So I created this scale here. I find this sort of thing worth doing. Now, then we added to the model the arsenic level. The arsenic level it had to be above 0.5. 0.5 was was the official threshold for it's too dangerous in Bangladesh, you're not supposed to have it. So, I mean, in a rich country, the threshold, like in the US, the threshold's 0.1. In Bangladesh, it's 0.5 because they're poor, so they can't afford as much public health as we can in the US. Here's the model. Being further away makes you less likely to switch. Having a higher arsenic level makes you more likely to switch. We made these curves. So again, I felt like I couldn't understand this model until I had the curves. So this shows the probability of switching as a function of distance among people with 0.5 arsenic level, which is the lowest possible that's dangerous, and an arsenic level of 1. And you could also have an arsenic level of 2 or 3. It goes up. So the higher the arsenic level is. Now we can also plot it the other way. So now I applied the probability of switching as a function of arsenic. And here are people who are 0, and here are people who are 50 meters from the nearest safe well. The arsenic levels are mostly between 0.5 and 1, but some people have arsenic levels as high as 8. If your arsenic level is 8 or 9, you should definitely switch. I mean, you should just, like, it's really bad. You don't want to be drinking that stuff. And indeed, the people with arsenic levels that were very high were more likely to switch. Now, if you only get one thing out of this course, the one thing you should get is that when you fit a regression model, you should take your 2 largest effects and interact them and try them out. I mean, that's just a good rule to do. Everything interacts with everything else. I struggle to come up with a theoretical explanation for why this should be the case, but in practice, it's clearly true. So we put in the main effect for distance and for arsenic and the interaction. Now, I always have trouble interpreting these things. What does this negative number mean? So you just sort of have to work it out. So it's like, this coefficient, dist 100, this is the coefficient of distance if arsenic is 0. This coefficient of arsenic would be the coefficient for arsenic if distance was 0. Because the model is 0.5 minus 0.58 times distance plus 0.56 times arsenic minus 0.18 times the interaction. So the interaction drops out if either of the main effects is 0. So this is not an interpretable model. And why I can't interpret it is because distance is never 0. You're never 0 meters from the nearest safe well. And arsenic level is never 0. Arsenic level is always at least 0.5. So whenever you have a model with interactions, you want to center the predictors first. So I created a new variable where I took distance and I subtracted its mean. I took arsenic and subtracted its mean. So these C stands for centered, so they're centered variables. Then I made a new model here. Now I can interpret this. So the coefficient is minus 0.88. So among households with an average arsenic level, increasing distance decreases your probability of switching by a certain amount. Among households that are an average level of distance, an average distance, increasing the arsenic was increasing your probability of switching. Now, how do we interpret this interaction? What I'm going to do is I'm going to start with the distance coefficient, minus 0.88. So that says for an average arsenic level, this tells you how much an increase in distance corresponds to a decrease in your logit probability of switching. As my arsenic level goes up, I start to add in these negative numbers. So that means the higher the arsenic, the more important distance is as a predictor. So it's actually sort of a positive interaction in that sense, even though it has a negative coefficient. So you can't, like, if you want to interpret it, you just have to be a little bit careful. And, okay, it's actually not statistically significant. But, you know, that's sort of a separate issue. Like, forgetting about significance, if you can't interpret it, then you're sort of dead. Now I graphed the model with the interactions, and here it's showing, you can see it. You see, here is the probability of switching as a function of distance. You see, the higher the arsenic level, the steeper the slope, right? And so that's what I was telling you. And you know, one doesn't want to overinterpret things, but you could sort of argue that this makes sense, because what this is saying is people who are far away seem to be not very likely to switch no matter what. But if they're close, so they're in the range where switching is a possibility, then higher arsenic levels are sort of motivating them to go to the trouble of doing it. Well, these are just survey responses. They're motivating them to say that they would switch. We can also look at the other way. Here's your probability of Here's your probability of a switching as a function of arsenic level for people of different distances.
Why don't you go back once again to the interaction?
Yeah.
Is it clear how it works?
Grazia says, "Is this clear?" Do you want to interrupt? Do you want to ask a question or comment? Okay.
I have a question on the graphical representation.
Yeah.
What are the bands on the top and the bottom?
The bands on the top and the bottom, those are the data. Each dot is a household. So these are households that didn't switch, and these are households that switched. So I'm showing, I always liked, well, I've jittered them a little so they're not all. So see, what I do, I always like to have a graph where I have, I like to have a graph with the fitted model and the data together. You should have asked this question earlier. You. Everybody else is off the hook, but. So I like to have a graph like that and see the model and the data. But in this case, the data are zeros and ones because they're just people saying they switched or not. So here are the raw data. And of course, I couldn't put them all at 0 and all at 1 because they'd be on the axis, so I jittered them a little bit. It's sort of a crappy graph. Like, it doesn't really tell you much because the data are all at the extremes and the probabilities are in the middle. But I still like to show that the data, see where they come from. And you can learn a little, like if you sort of, you can see here are some unique data points. Yeah. But I wouldn't claim it's the best possible visual representation. Yes?
Why didn't you use the log on the x-axis to stretch the data?
Why didn't I use the log? I actually did use the log later. I'll get to it. But why did I not start with the log? The reason why I didn't, I mean, I'll sort of get to that too, but it seemed to me that it should be linear because every additional, all they're doing is walking, so every additional 50 meters or 100 meters is an additional fixed amount of effort. So it seemed to me logical that the difference between 0 and 50, 50 to 100, 100 to each of these should be a constant effect. Similarly, the risk of getting cancer is linear with arsenic exposure. So to my mind, when I built this model, I thought these should be linear because it's sort of the opposite of that tree bush example. Here, logically, it should be linear. It shouldn't be on the log scale. Going from 4 to 8 is much worse than going from 2 to 4. And going from 2 to 4 is twice as bad as going from 1 to 2. So if I had done that in the log, no, of course, I could have made the graph on the log scale, but I wanted the model to be linear. But I'm actually going to get back to that. But first, I added a couple more predictors. So we had centered distance, centered arsenic, the interaction. Then I added whether you were a member of an association or not, and your education level. Educ 4, that's your education level in 4-year units. So education was the number of years of schooling, so it's typically between 0 and 12 or 16. So again, like, what's the effect of one more year, the predictive power of one more year of schooling? It's sort of too small to interpret. But 4 more years I can interpret, because that's like 4 years of schooling is like 1 unit of school, right? You're the first half of primary school, the second half of primary school, secondary. So I did that. Now, in higher educated people were more likely to switch controlling for all these. Association, I just threw this out because it was not significant and it was the wrong sign. So it was like, I don't believe it. Now, you know, you're not supposed to say that you do stuff like this, right? Because this is like I'm deciding it looks wrong. If this had been positive, I would have kept it in, even though it wasn't significant, because I would have said it makes sense. But if it's negative, I'm like, yeah, I don't buy it. Like, it seems very unlikely that people, you could come up with a story. Like, if you're a member of a community or association, you're a high status person and you don't want to go knocking on your neighbor asking for their water because, maybe there's a reason for it, but I didn't really believe it. It's just a small sample phenomenon. I just thought it was just one of these things. So I didn't think, I was suspicious that it would generalize, so I didn't include that. Yes.
There is a risk, perhaps, in trying to say that I believe in this parameter sign, so I put it in the model or not, being very subjective in the analysis.
Oh yeah, so there's risk. So by throwing out that coefficient, like, sure, but there's so much subjectivity in just what you put in your model in the first place that I want to go with what I think is best. I mean, I would definitely recommend that another survey be done if this was going to be transferred to the policy level. Again, it's not hard to do another survey. In my analysis of these data, I wanted to do as good as I could, though. But yeah, I think you just have to write down what you do. You have to say, this is what we saw, and we felt that this was not particularly plausible. Again, the purpose, remember this, the goal is not to learn about the sample, the goal is to learn about the population. So a negative association in the sample, just means that the particular people in the sample who happen to be members of community associations happen to be less likely to say that they would switch for whatever reasons. I have no particular reason to suspect that would generalize. But I could be wrong, indeed, I have uncertainty.
Yeah, sorry, on the same line, actually, belonging to a community could also be that you are less free to decide autonomously, and maybe the community could be conservative in that place. So,
Yeah.
could also leverage some actions not for the single person, but maybe on the communities. But just thinking.
No, I think you're right, and in fact, for that matter, it suggests that the whole procedure, maybe a future study should ask more than one question. Like, they could ask, would you switch? But they could also ask, would you recommend that it be a general policy that everybody switch? Something like that. Like, it might be that we're framing it wrong. I mean, let's take another example, which is cigarette smoking. There's a funny thing, it's very hard to get people to quit smoking cigarettes. You can offer people all sorts of incentives and they don't do it. But yet, the rates of cigarette smoking vary a lot from country to country and from state to state within a country. It's in some sense, it's easier to get masses of people to quit than to get a single person to quit. Right? Like they make smoking illegal and less popular and people stop doing it, even though individuals can't do it. So it's a paradox that it can be easier to change the behavior of millions of people than to change the behavior of one person. Because at least in the US, we have this very individualistic way of thinking. And so that it may be that the very framing of this survey is really missing the point.
I have doubt on making the decision based on the sign, because for sure you can define an indicator that is saying how lonely are these people. So exactly the same indicator will come to plus instead of minus. But I would like to do one step back, because in your discussion you are saying, let me also link what our colleague is saying. I think, I suppose, to my mind, it seems to me that this makes sense to include or not. But I think that that you should define a common language with a subject matter expert. So, for example, here is a kind of Indian society expert, or a kind of people that knows how the pipes works, etc., and to define the common language to take such a decision together with the subject matter expert, either to have a more, let me say, automatic way to take decision on the parameters.
Oh, well, yeah, I mean, I did not do this on my own. I mean, I was working with an economist who was working with people from Bangladesh. So it's not, in that sense, it's, I mean, ultimately you got to think, like, what was the purpose of this? So I think in a way, the point was not to predict individual behavior here. We were coming in saying, we have a recommendation. And our recommendation was that people consider switching. So if you're going to make that recommendation, you want to say how many people are going to switch. So in some sense, the number one thing that we got out of this survey was that half the people said they would switch. So half the people is either a big number or a small number, depending on how you look at it. But that's really the starting point. And then you say, well, who were these people? Well, they tended to be people who had worse arsenic, who were closer. You know, so that suggests that it could be useful to alert people to the fact that there's a nearby well. And it could be helpful to tell people that their arsenic level is high. And, well, education was predictive. Like, so it's sort of, like, we're inferring from the survey, and then the connection between that and policy is fairly indirect. So in that sense, it's a little different than some of these studies that I led off with an hour ago. Like, it's not so much that we're trying to prove, you know, we're saying, well, this is statistically significant, so we've proved that people with higher arsenic levels are more likely to switch, and let's publish that. You know, it was much more like if a policy like this is supposed to be implemented, then let's try to understand who would do it. But then, you know, I don't know what's been happening. I mean, this was years ago that we did this. So I mean, it's also like a lot of research that, like, you know, this was a direction that we were working. We had this idea that because what was happening was people started realizing that they had arsenic problems, and so everyone wanted to measure their arsenic levels in their well. So we had this realization 10 years ago that if everybody measures it, then all of a sudden we'll have this great database, and then we can tell people where the safe wells are. But then I don't know what's been happening more recently, because there was another thing that we were doing, which was telling people where to dig deep wells that don't have arsenic. So then, if you know, digging your own new well, that's even better than switching, right? So I don't know where this all stood, and I mean, also yeah, but anyway, still a good example of logistic regression, I guess. So here we are with the model that we were going with, a little bit simpler than the last one. So I said we should try interactions. So in this model, we interacted distance and arsenic, but I thought let's interact them with education. So you can throw in more of these things. I centered education, and now everything's interacted with everything else. And you know, some of these are pretty big also. And you know, just like, so we've already interpreted this one, so let's look at distance times education. So the way to interpret this is to say the effective distance is negative, right? So the further you are, the less likely you are to switch. But now, when you're more educated, you add a big fat 0.32. So actually adding 0.32 makes the minus 0.9 less negative. So what it says that if you have more education, distance is less of a factor in you deciding whether to switch. And here, if you have more, if you have more education, it's saying that arsenic is a larger factor. Now, again, I don't know if this would replicate. It's not statistically significant, but it's somewhat of an appealing story. The story is that if you have more education, you're like, well, I'm just going to do it, but how I'm going to be willing to put in the effort to walk anyway. Distance is less of a factor, but arsenic is more of a factor, which sort of is appealing because if you have more education, then the numerical level should matter more. Again, it could be wrong, but if you can, sort of understanding the predictions of the model is the key first step. If you can't understand it, then it's silly to start arguing about statistical significance because you don't know what you're even arguing about. Now, this is a, oh, okay. Oh, it's 5, okay. Relax, stretch your legs for 5 minutes. Thank you. Households where it was predicted based on your predictors that you were very unlikely to switch. And there were some where it was predicted that you were very likely to switch. So these people would be like households that are very close, that have very high arsenic levels and are very close to a safe well. These would be the opposite. And the residuals, the average residuals show no clear pattern. So this is sort of nice. But I wanted to make a couple more graphs. So here I'm plotting the average residual versus the probability of switching from the model. Now I'm going to plot the average residual versus the distance to the nearest well. So some people are very close to the nearest well and they're supposed to be fairly likely to switch. Their average residuals are close to 0. Again, the dotted lines are plus or minus 2 standard errors. So it makes sense that occasionally you'll have a point that is 2 standard errors away. We've divided the data into 40 equally spaced bins here. So each bin contains 1/40th of the data points. That's why there are fewer dots here and more over there. So no real pattern, which is as one would hope. Then I plotted the average residual as a function of arsenic level. And not much going on except here. There are certain households where the arsenic level was at 0.5 or very a little bit more than 0.5, right at the safe level of whether it be dangerous or safe. And these people were much less likely to switch than the model predicted. So this indicates a model error. You're not really supposed to get a point that's 4 standard errors away like that. So it indicates a problem. So sort of looked at this. I was thinking about this. So somehow, if your arsenic level is just a little bit over 50, you're less likely to switch. You're already less likely to switch, but you're even more or less likely to switch than the model would say. And I thought of doing a log transformation at this point on the arsenic level. And so the idea was that these low levels, I don't know, that it's hard for me to say this in words, but when I saw this pattern, it struck me the logarithmic transformation that would make sense. It would basically stretch out this part of the data and allow these cases to have a higher probability of switching. But it's, as I said, it's hard for me to express it in words, so let me just show you what happened. So this is the same graph, I just stuck it up there. So we fit the same model as before, but now everything was in terms of the log of your arsenic level. The model looks like it did before, except now the predictor is not your arsenic level, it's your log of the arsenic, and that's interacted. The model actually, qualitatively, it looks like what we had before. The signs of the coefficients are actually the same. They don't have to be the same as we talked about before, but they are here. Here's the old model and here's the new model. Now look what happens. Here's the model as a function of arsenic, and here's log arsenic. So what happens is when it's on the log scale, but I didn't plot it on the log scale, I'm just fitting it on the log scale. So on the log scale, going from 0.5 to 1, or from 1 to 2, from 0.5 to 1 is equivalent to going from 1 to 2 or to 2 to 4. So changes, you see there's a big change near the beginning. It's a very steep slope here because on the log scale these are relatively large changes, and here it's flatter. And if you start staring at this, it does fit the data better. In particular, it curves down sharply here, and remember the old model, there were too many, in the old model people were not, the residuals are negative, meaning people weren't switching enough, so you sort of want it to pull down. You could do even more by doing log of x minus 50, but that would seem like a cheat, sort of, right? So we're doing log of x. And then at the high end, on the original model, you notice that people are having like a 99% chance of switching if they were at the top, if they had high arsenic levels. You see that at the top of that graph? But if you actually look at the data, look, there are some people with high arsenic levels who aren't switching. So it's not really a 99% chance of switching. The model's not even fitting that well. In this case, it sort of flattens out. Because it's on the log scale, an arsenic level of 8 is not that high. So this model actually better explains these points. So all around, it's a better model. in terms of the data. I'll talk about substantively in a moment. Now we refit the model, and now we looked at the binned residuals again. There's still a problem. There's still something going on. The people whose level arsenics are right around 50. And I just wonder if this is like a psychological effect. Like if your arsenic level is 51, maybe you feel like it's practically safe, so you shouldn't switch. Like maybe there's something like that going on. Again, as I talked to somebody in the break about this, what you really want to do is some qualitative interviewing. I mean, I would love to go back to these people who said I wouldn't switch and ask them why. Like, why wouldn't you switch? There's stuff that's like killing you, man. And then maybe they would say, well, maybe they would say, I don't think it's that bad. My measurement's 50. Maybe they would say, I wouldn't switch because I'm digging a new well. I'm digging a new well in my backyard next week, so I'm not going to bother switching. You know, you don't know why. Like, people have good reasons for things, and especially personal behavior. Like, it makes sense to follow up, and we didn't do that. And one of the problems with statistics is you end up focusing on the data you have, and you forget about the data that you didn't get, that you could learn about. On the other hand, I think we learn quite a bit from these aggregate data that you wouldn't learn from just a bunch of interviews. Okay, so to continue, we stuck with this. The model's not perfect, but this is what we stuck with. Now I want to sort of talk this through. Distance to walk comes in linearly in the model. So the change from going from 0 to 100 meters is the same as 100 to 200 or 200 to 300. I think that makes sense because every 100 meters is an equal amount of effort on your legs and your arms, right? Arsenic now is coming in on the log scale. And so what I wanted to say, does this make sense? Psychologically, I think this makes sense. So psychologically, an arsenic level of going from 1/2 to 1 or 1 to 2 or 2 to 4 or 4 to 8, each seems like equally equivalent in your psychologically. Now physically, that's not true. Physically, I mean, let me put it another way. Suppose I told you had an arsenic level of 1, and you could take it down to 0, okay? And then I told somebody else they have an arsenic level of 8 and they could take it down to 7. Going from 1 to 0 sounds really great, right? Going from 8 to 7 doesn't sound like such a big deal, but it's actually just as good. It's actually just as good for your body to go from 8 to 7 as to go from 1 to 0. But people don't think of it that way. So I think this is, like, I might be reading too much into what we got out of one little data set, but I felt very satisfied when we got to this because I felt this made sense. Maybe I should have started with the log scale, but I hadn't thought of it. I was really forced to do it by the data not fitting on the linear scale. Then there's interactions. I'm not going to keep yapping about them. Okay, so in summary, with logistic regression, we built the model by starting with something simple and then adding things. We didn't start with the big model because we wouldn't have been able to understand it. We checked the model using graphs, and you notice it wasn't until the third graph that we found the problem with the model. So it wasn't that we just like tried one thing. We kept looking at it from different angles, we tried to perturb the model to see where it went wrong. And of course, we're always improving the model. We're never stopping. Now, next I want to talk about choice models, and this is sort of the psychology or the economics connection to logistic regression or probit regression. This is very important. For people who do social science research, like when I teach political science students, this is very important because these are sort of the decision models that underlie the statistical models. So I'm going to go back here. This is our arsenic model. A probit, do you know what probit regression, you heard this term? I feel like, I hate to waste your time on this one if you haven't heard. Well, probit regression is like logit regression, except the coefficients all get divided by 1.6. Otherwise, it's the same thing. It's like logistic regression with normal errors. I don't want to try to define it all for you, but I have to do a little equation because this is actually sort of, I hate to do any equation at all, but this is sort of crucial to understanding. So this is logistic regression. The first line is your basic logistic regression model. The probability of switching is the inverse logit of this linear combination x beta. The inverse logit takes the linear predictor and scrunches it onto the 0, 1 scale, so you get a probability. Now there's something called the latent data formulation of the model, in which we say that what we observe, our observation is, sorry. We observe a 0 or a 1, but there's an underlying variable, a latent data variable we don't observe, which is z, and z is a continuous variable. Wait a sec. So each person has a continuous variable z, and here's 0. And if z is greater than 0, then you switch. And if z is less than 0, you don't switch. So z is sort of some number which is like, how switchy are you? So if z equals 0, you're poised between switching and not switching. You're completely indecisive. If z is like 0.2, then you're slightly likely to switch, but you're sort of ambivalent. If z is plus 5, then there's a 99% chance that you would switch, basically. I shouldn't frame it that way. Let me not say it's a 9. If z is plus 0.5, you're a very strong switcher. So the analogy that I like to use, because I'm a political scientist, is political ideology. So if z is how far, this is you're on the right and this is on the left. Everyone over here votes for the right-wing party and everyone here votes for the left-wing party, because in the US we only have 2 parties. But if you're right here, you're just very slightly right-wing. If you're over here, you're extremely right-wing, and so forth. You guys are probably all over here because that's how it works. And the idea of this model is that you think of z as having some sort of fundamental meaning. Okay. Z is your linear predictor plus an error, and you don't observe this. In the logistic regression model, the error is approximately normally distributed with a mean 0 and variance 1.6 squared. The probit model, it's normal 0, 1, which is sort of amusing if you use these models, and if you don't, it doesn't really matter. But what is important here is that we think of each person as having this latent z, but you don't observe it. So all someone tells you is, I will switch or I wouldn't switch. It's like they would say, people will tell you who they would vote for, but you're not asking them how strongly they feel about it. Well, here's the political example. So in the political analogy, the outcome is whether you would vote for the Republican. Z is your latent, yes?
The threshold, is it always 0, or for some calculation of risks and benefits, it could be somewhere over 0 or before 0?
Well, we'll get to that. So if what happens is, suppose this number is not 0, suppose the threshold depends on certain cost-benefit calculations, you could throw the threshold into the constant term in the regression. So it becomes redefined as 0. So here, in the political example, I should have shown this slide earlier, I guess. Z is how Republican you are. And the one point is that you can actually measure it. So you can ask people a question like, would you switch? How strongly do you feel about it? Or you could say, how strongly do you feel, how much do you support the Democratic and Republican parties? Give me a number between 0 and 100 to tell me how strong you feel. So you can sort of measure Z directly. And then you can model it in various ways. And people do this all the time in political science and economics. I mean, in economics, it's, another example would be that what they call the reservation wage, like how much how much money that you would accept to work at a certain job. Something, if someone accepts the job, you know that the job is worth at least how much they want for it, but you don't know how much. You only observe that it's greater than a certain threshold. Now, what I'm going to do here is I'm going to demonstrate how logistic regression corresponds to a very specific model of decision making. So I'm going to take this simple model in which the probability of switching only depends on how far you are from the nearest well. And so now I'm going to look at your decision of whether to switch. So your household I, I'm using a subscript to indicate households. You will switch if the benefit exceeds the cost. So the benefit of switching is proportional to your arsenic level, right? Because the more arsenic, you have, the more you gain from switching. Right? The cost of switching, there's a fixed cost because you have to, go carry a bucket of water and talk to your neighbor. And then there's a cost of switching that's proportional to distance walked. So this C is a very important coefficient here. So this letter A corresponds to how much you care about the cancer risk. And this C corresponds to how expensive it is for you to walk. And then you switch. Well, what's the probability you switch? You switch if the benefit exceeds the cost. So you switch could be expressed in terms of this distance x. You switch if A times your arsenic level minus B over C is greater than x. So probabilistically, this is just a restatement of the model in decision terms. So here you have a decision. Here's the benefit, here's the cost, here's the probability of switching. Mathematically, the probability of switching depends on the distribution of this term, which is the cost minus the benefit the benefit minus the fixed cost divided by the per meter cost, or per 100 meter cost of walking with the water. This thing has a distribution, and the distribution induced by this gives you your logistic regression. And as long as this thing has an approximate normal distribution in the population, you'll get logistic regression out of it. And I'm sort of feeling bad about this part of what I'm telling you, because I think I'm sort of saying it too fast for you to follow all the details. So I probably shouldn't be doing it. So maybe I'll just skip this, because I don't think this is being very helpful. So I'm going to skip this, and skip this, and I'll skip that. So let's forget we did the choice model. I think that was sort of a waste of time. Sorry, I apologize for that. Let me now summarize where we are. I feel bad because that was like 15 minutes. So let me just say something about it, because that, okay, so in social science, these logistic regressions models for individual behavior, logistic regression model, in a lot of social science, especially in political science and economics, when you're modeling individual behavior, it's done based on a cost-benefit calculation. And when you fit a logistic regression, you can interpret that as saying that corresponds to a certain distribution of perceived costs and benefits in the population. So the point of this last example was that if you wanted to make those social science assumptions, you can deduce something about people's perceived risks and benefits given the logistic regression coefficients. And it's sort of cool, but I don't always really believe it. And often the reason I teach it is because within the world of social science, it's considered important. But I think I didn't really have my heart in it this time. So anyway, I'll stop talking about that, okay? Let me talk about where we are so far. The key message, I think, was that, well, let me do this slide and then, okay. So I think if you want to abstract everything that's gone so far, it's that a model gets built, I feel like in your training, it's usually, you don't think of it that way. Like, first you take a theoretical statistics class and they say, data y1 through yn have a Poisson distribution. How do you compute the maximum likelihood estimate? There's no, you don't create a model, right? And then later on you have regression. And what they tell you is, here's data and here's a bunch of x's, and now you run a regression. And actually, we really construct the model. We don't, there's no virtue to taking the data out of the box. We transform, we select, we combine predictors, we break things up. All of that is central to what we do. It can't be avoided. And we should spend a lot, we can learn a lot by checking the fit of our model. So checking the fit of the model, it's not about like, I don't know how to say, like it's, the reason for checking the fit of the model, it's not like some silly game like you do a residual plot or whatever, put a quadratic term in or something like that. The reason is that there's often more in the data than you realize. That even that little data set has a lot of information if you can sort of know how to look for it. Now, as we talked about at the very beginning, you can overinterpret things. So one has to be careful. Really, you have to replicate and get new data. But it makes sense to check the fit of a model, I think. Now, tell me what was your comment?
Sorry, because my question is about what you have just said.
Yeah.
You don't want to speak.
No, but yeah.
My question is it difficult to understand a global attitude towards risk or cost and benefit, especially in politics? Because for me, it can be a utility curve different from you or another person. So, how statistics can be applied in a so varied world?
So the question was like, how could we use statistics to measure attitudes towards risk or utility functions, given that they vary so much from person to person? And I think, to me, I think these are really problem specific. So I don't think it makes sense to talk about individual person's utility function. Like sometimes people say like, what's your utility function for money? I don't think the concept of utility function for money makes any sense. I don't think it exists. I do think that there are certain situations, I mean, I think it's ludicrous. I think it's ridiculous to say that people have utility functions. I don't think it makes any sense. I hate that stuff, okay? But what I do think is that there are certain problems in life that are very clearly decision problems. So deciding whether to switch your well is a decision problem where people are pretty much explicitly weighing costs and benefits. And in a situation where people are already doing that, I think it can make sense to try to measure those things. For politics, you know, it depends. I think there are situations where people are trying to decide how to vote and they are trading things off fairly explicitly. But yeah, I don't think there's a global utility function to use. Yes?
I don't know, sorry if I come back to this example
Mm.
again, because for me it was a very nice example, because it shows a completely different approach than we took first. In the beginning we looked for any influential variables and we tried to make up our mind what could be the reason. And the second approach was we come up with a model and we derive assumptions from that, and when we start testing. But did we then test the validity of the model, or did we test anything else? So I think for me that is
Well, I mean, I think there are different ways of, you can derive a model by starting with an individual decision function and then say after you turn the crank, it turns out logistic regression is how to estimate it. Or you can start by running a logistic regression and then saying you could interpret this as, I mean, I think it's not terrible. I just think whatever I have prepared, I'm not really in the right mindset to talk about. I think I'm wasting your time to go through the slides, so I don't want to waste your time. I'm not saying it's bad stuff. Yeah.
So last on the
Yeah.
there was last topic on the agenda, continuous improvement. Would you mind spend some words on it?
Oh, when I say continuous improvement, I just mean like, you know, in this example, like I think the real question is, why are people not switching? And so I think you need to probably go back and interview people and find out. So it's not, I just felt like, it's not like, oh, we could say we found a statistically significant result so we can relax. Like, that's not the goal, right? The goal is to think about how to implement a policy. So there's never an ending point. And first, at the purely statistical level, our final model had a problem because it wasn't predicting quite right with people. People who had arsenic levels of 0.5 or 0.51, they weren't switching as often as the model said. So there's a problem there. But then just more fundamentally, there's a deeper problem, is that we don't really understand why people aren't always switching. And so we need more information. So it's not, that's all. There's always more to be done. It's not like you stop.